The worlds in our solar system are one of a kind. They may even be rare, but if we turn our eyes away from home, we'll soon discover that there are truly some weird worlds out there. Today, we won't be straying too far from home though. Alpha Centauri is a system made up of multiple stars. Alpha Centauri A, a sun-like G-type star, Alpha Centauri B, a smaller K-type star, forming a binary with Alpha Centauri A, and maybe a small outer red dwarf. It's unclear whether or not this red dwarf is gravitationally bound to the binary, but in either case, this red guy is the closest star to the sun, appropriately named Proxima Centauri. Proxima Centauri is home to potentially 3 exoplanets: a hot inner planet around twice the mass of Mars, a disputed super-Earth way on the outskirts of the system, with a potentially large ring system that we may have directly imaged, and the star of the show, Proxima b. It's a little bit larger than Earth, and it orbits in the middle of the star's habitable zone. The closest star system to Earth could be potentially habitable, or at least a very promising candidate for future explorations and potential far future colonization. But before we get to asking what life this planet could potentially have, we have to ask ourselves what this planet could even be like. Because the answer to that question is a lot more complicated than you'd want. The Proxima Centauri system is also very well known for its flares. All red dwarfs, like Proxima Centauri, are characterized for its flares, but Proxima is the poster child for severe flaring events. Back in 2016, 10 years ago by the way, astronomers observed a flare coming off of Proxima Centauri that, within minutes, made the star 68 times brighter. These super flares are predicted to occur around 5 times a year, but regular flares like those emitted by the sun are a lot more common, occurring multiple times a day. Again, flares like those emitted by the sun coming from a tiny little red dwarf star. If that wasn't bad enough for habitability, Proxima b's orbital distance is only 5% that of Earth's distance to the sun. This proximity to an ultra-active red dwarf star is going to obliterate any atmosphere Proxima b has in an incredibly short amount of time. Water would not survive in this scenario, let alone any life. Proxima Centauri b could be, at best, a world like Mars, maybe even more like Mercury or the Moon. Barren, desolate, irradiated, and dead. To complicate things even more, we don't even know how big this planet exactly is, only that it is a little bigger than Earth. Proxima Centauri's planets were discovered via radial velocity, which measures the redshift and blueshift of a star's light due to the planet's gravity tugging on the star as it orbits it. Now there is a problem with this method. We can only derive a planet's mass based on the whole star's back and forth motion. It doesn't take 3D space into account. Say we observe a star wobbling this much, causing this much spectrum shifting. This could be due to a small Earth-sized planet orbiting edge-on with the star, but if the planet has any sort of orbital inclination, which is a lot more likely, then a lot of the star's orbital motion would be up and down motion, not the back and forth that radial velocity can detect. Meaning that, in order to reproduce the observed back and forth motion, the planet would need to be much larger. So, we only know Proxima Centauri b's minimum mass, around 5% more massive than Earth. In order to figure out how truly big this planet is, we need to figure out how inclined its orbit is relative to Earth, and we could kind of guess that. The rotational axis of Proxima Centauri is around 47 degrees as observed from Earth. If Proxima Centauri's planets orbit along that same plane, which they should, that gives Proxima b a refined mass of 44% more massive than Earth. Not that much bigger, but it's a big difference. But that's not the full story. We also need Proxima b's radius in order to figure out its density and potential composition, whether it has a rocky composition with a large iron core like Earth, or not. Unfortunately, none of Proxima Centauri's planets transit the star, which means we don't have a figure on any of these planets' radii. But we do have like thousands of other exoplanets, several of which are around the same mass as Proxima b, and taking a look at those, we get radii between 0.95 and 1.35 times the radius of Earth. This rather wide range of radii gives a wide range of potential compositions, ranging from those mostly made of iron, again like Mercury, to a planet made of silicate rock with an iron core, like Earth or Mars, and even lower density planets potentially being made of water or gas, like a mini Neptune. However, we have to consider Proxima's flares too, so mini Neptune probably isn't the option. If we take another look at the exoplanets the same mass as Proxima b and compare their radii, the most likely scenario for Proxima b is a rocky composition, either with the smaller iron core compared to Earth or more water compared to Earth, kinda like the TRAPPIST-1 planets. I imagine this scenario as an ice world. No atmosphere means no liquid water. But various climate simulations of Proxima b have determined that it does have regions that are above the freezing point of water. Any ice in these regions would vaporize directly from a solid into water vapor gas, which would end up as snow and sublimating back down into ice in colder regions. Kinda like how carbon dioxide dry ice behaves on Earth. Now, as a reminder, none of this is based on observation. These are all my predictions based on one very loose data point. We don't know if Proxima b has any water, let alone a substantial amount of it. And to pile on top of all that, we don't know if water can form as a liquid on its surface. Whether or not liquid water can exist here depends on if Proxima b has an atmosphere or not. But with Proxima Centauri's extreme flares, that looks pretty unlikely. But Proxima b is a slightly bigger planet than Earth. Maybe it has more gravity that could hold onto an atmosphere despite the flares. And up until this point, I made it sound like flares equals death, but is it really that black and white? Just how likely is it for Proxima b to have an atmosphere? In order to answer that, we need to revisit the cosmic shoreline. The cosmic shoreline is a rough determination of how likely a planet is to retain an atmosphere based on its escape velocity, determined by its mass and radius, and how much UV radiation it gets from its star. This graph is just one approximation of the cosmic shoreline, but anything above the shoreline, in red, is less likely to have an atmosphere, but anything below the line, in blue, is more likely to have an atmosphere. We can kind of guess the escape velocity based on the mass and radius we kind of have, and within any given time, Proxima b receives between 10 and 60 times more UV light than Earth does. All of these values places Proxima b right here. If we assume an average middle ground of like 30 times more UV than Earth, that puts Proxima b where that middle dot is. But come on, this range is a perfect 50-50. I mean, I wish I was recording my live reaction when I made this graph. It's like we're writing a fucking comedy right now. You're just trying to fuck with me. But I guess from what I can gather, either Proxima b doesn't have an atmosphere, or it does. That's as conclusive as I can get. But fellas, there is yet another complication to all of this. The cosmic shoreline tries to quantify atmospheric retention if a planet can hold on to an atmosphere. It doesn't take into account whether or not a planet can generate an atmosphere, such as through volcanic activity. In other words, how likely is it for Proxima b to have volcanism? Like most planets around red dwarfs, Proxima b orbits very closely to Proxima Centauri. This would subject the planet to extreme gravitational forces from the star, resulting in a phenomenon known as tidal locking, where one side of the planet always faces the star and the other side away from it. If the planet's orbit is in a perfect circle, which is very likely, those same tidal forces will also cause stretching and squeezing of the planet's interior. This creates friction within the planet's interior, which leads to tidal heating, and then volcanism. This is a very common talking point on this channel, but something about Proxima b is different. As of 2021, the planet's orbital eccentricity is low, but not a near circle kind of low. Some studies put Proxima b's orbital eccentricity at around 3 times greater than Earth's at most, but it could go as high as Mercury's eccentricity. This will introduce a substantial amount of tidal forces on the planet, leading to levels of volcanic activity compared to that of Io. Whether Proxima b has an orbital eccentricity that of Mercury or Earth, tidal heating should produce enough volcanic activity to generate an atmosphere on Proxima b. Even if it does get stripped away by Proxima's UV flares, the volcanic activity could be substantial enough to replace that lost gas with something of an atmosphere. Again, there's no real way of telling how dense this atmosphere would be, let alone if this place actually has any volcanic activity at all. But if it does, this atmosphere would be made of volcanic gases, carbon dioxide, sulfur compounds, and water. If there is enough of an atmosphere for liquid water oceans to exist on Proxima b, then the tides will have fun with these as well. According to a paper published in 2025, which assumes an orbital eccentricity of 0.3 for Proxima b, any oceans on this planet would have tides a kilometer high. Okay, well, the 0.3 orbital eccentricity is a bit high. It's likely around 0.1 or less, but this paper also simulated other exoplanets with lower orbital eccentricities, and determined that the tides for those planets should be at least comparable to those on Earth, and at most hundreds of meters high. Which is still a lot. For this scenario, I'm imagining a world covered in basalt and ice, dotted with supervolcanoes. On the day side of Proxima b lies a small blue sea. As Proxima b moves along in its eccentric orbit, the 100-meter high tidal bulge will sweep across the planet. Whatever isn't a glacier or a volcano would either be crushed by a high tide or drying off, recovering for when the high tide returns in a mere few Earth days. But there is still a pretty big chance that Proxima b is going to be covered in a large amount of water, which would result in our ice world scenario. An ice world is favored, 1, because of its low chance of holding onto an atmosphere, and 2, it's quite cold, only receiving around 2/3 as much light from Proxima Centauri as Earth does from the sun. Now, a tidally heated ice world is something that we have seen again in the solar system. Look at Saturn's moon Enceladus. But that potentially high orbital eccentricity for Proxima b is, something I can't ignore. And if it is on the table, then those extreme tidal forces may do more harm than good. Another paper, published in 2023, discusses our prospects for finding any potentially cryovolcanic exoplanets. To do this, they chose exoplanets that were predicted to have a low density and a substantial amount of tidal forces, such as those orbiting red dwarfs or that have high orbital eccentricities. Proxima b fit the bill perfectly, so it's in this paper. Then, assuming an orbital eccentricity of 0.1-ish, the paper then calculates how much tidal heating Proxima b would be experiencing, among other exoplanets. And oh, I wonder what that big fucking blue bar is on the graph. Oh yeah, that is 20 times more internal heat than Io. There are a lot of implications for what Proxima b could be like based on these results. Let's see what the paper itself has to say first. Proxima Centauri b may be similar to Io's volcanic activity. Okay, very similar. Come on, bro. That is 10 times more, 20 times more. High rates of cryovolcanism through geyser-like plumes, effusive cryolava flows at their surfaces. Cryolava. Call it... it's just water. And cryomagnetism in the form of upwellings and convection in their interiors. Ooh. Oceans on these planets would be located fairly close to their surfaces, as the case for Enceladus. Proxima b are especially notable as their oceans would lie less than 100 meters below. Wow. So the bit I just talked about, the substellar ocean that's very close to the surface, that depends on the temperature, that's what they talk about here. The paper assumes that Proxima b has a albedo of 0, which would mean warmer temperatures. Probably not the case, but let's see what this has to say. Newly calculated equilibrium temperatures are substantially warmer than those previously cited in literature. Corresponding depths to ocean layers decrease on all of these worlds. An ocean on Proxima b, for example, would be 4 meters closer to the surface. Wow! Sort of the same point here. For example, depths to oceans on several planets, including Proxima b and the TRAPPIST-1 planets, are 2 to 3 times larger when considering albedos and emissivities identical to those of Enceladus. Enceladus is like very bright. It has a very high albedo. And that's because of fresh ice. I'm not sure that'll be the case with Proxima b. Maybe. The cold ocean planet in our study that experienced the most tidal heating raises the range of equilibrium temperatures to cold to fucking hot. What the hell? Suggests that Proxima b could have an icy surface, perhaps with transient pools of liquid water, or slush in regions of the planet where tidal heating is concentrated. Oh! Despite Proxima Centauri's high levels of cellular activity, Proxima b is likely to have retained significant amounts of water, and that its surface may partially be or covered with ice, global or regional oceans, lakes, or a combination of these. Wow! We note that tidally locked planets with non-zero eccentricities, like Proxima b, will not be in synchronous rotation. Therefore, any planets with significant tidal heating will not have permanent day-night sides. Holy fuck. 324K. Oh my god, that's bad. That's not good. Huh. The output of water vapor from geyser like plumes is that. The estimated water output for tidally driven volcanic eruptions on Proxima b far exceeds this value. Far exceeds Europa. But it would still be too meager to form collisional atmospheres on this planet. As it is honest. Huh. The reason why they're talking about exospheres is because that's the part that's going to escape the planet. That's the part that we are most likely to detect. And that's the point of this paper, is if we can detect cryovolcanism, not whether or not these planets have like substantial atmospheres. And that's more of a point here. See, at first glance, Proxima b would appear to be the best candidate for detection of cryovolcanism, but yeah, it doesn't transit. And apparently, the Hua, which is in development, can't detect it either. Likely to be interior of the inner working angle of the future coronagraph instrument. Direct spectroscopy instruments like the extremely large telescope, again, future. Ooh, induction heating. We talked about this before. Induction heating is the process of an object made of metal, like a planet's iron core, moving through another object's magnetic field, like Proxima Centauri's magnetic field. That will heat up the planet, heat up the interior, volcanism. Induction heating may have played a major role in the outgassing and internal heating of Proxima b in its early evolution. Though, whoa, it does talk about atmospheres. Like actual atmospheres. Proxima b could have an appreciable atmosphere dominated by carbon dioxide, nitrogen, or oxygen. Okay. Carbon dioxide is also normally frozen at the minimum surface temperatures explored by Proxima b. Atmospheric collapse is a possibility. Yeah. Now, a lot of that is just to say that Proxima b could be any variant of Ice World, or maybe even something like Earth. But those potentially high temperatures and comically intense tidal heating is tipping me off. In the abstract, they call Proxima b explosive. I'm not even sure where to begin to imagine this scenario, but I can try. Proxima b could be experiencing so much tidal heating that it turns out to be a Venus-like world. Volcanoes everywhere, erupting all the time, which yeah, would generate an atmosphere, but there would be so much volcanic gas that a runaway greenhouse effect would occur. Whatever water that does exist on this planet would be in the form of water vapor, contributing to a thick steam atmosphere. Water vapor is also a very strong greenhouse gas as well, which would heat the planet up even more and make everything here a lot worse. That's if this planet has water, and if this planet has a high eccentricity, and if this planet has a bunch of volcanism, if. You know, you'd think for the closest exoplanet to the solar system, we'd know more about it. All that we've really observed about this place is Planet B's gravitational influence on its host star. None of the planets transit Proxima Centauri, and they orbit too closely to be directly observed. And this isn't a problem with the Proxima Centauri system. Most of all exoplanetary systems we know next to nothing about. This whole Weird World series is just me speculating. Even if it is like educationally informed by like research papers, either I use those papers to fuel my speculations, or the papers themselves are based on assumptions we make about the planet. So yeah, while we are technically working with cutting edge technology, with even better technology coming in the near future, there's still a long ways to go, and a lot more that we can learn. All that we can say for certain about Proxima Centauri b is that we know nothing about this weird world.
Hey Elijah, I haven't seen you in quite a while. Do you still sing that song of yours when you fly around? Oh, I miss your voice in the morning before the light arrives. Oh, I think of you in the morning, and I don't even try. I don't even try to. I never said goodbye. It's too late to find you. It's too late to find you. It's too late to find you. So hey Elijah, don't know how to tell you, but I've been running out of so crazy trying to find